Welcome to the whiteboard for this explainer. Grab your brightly colored mental markers because today we are sketching out humanity's ultimate engineering blueprint. We're talking about capturing the sun's endless fire. It's a megastructure so insanely huge, we literally have to dismantle an entire planet to build it. Yep, we're building a Dyson Swarm.
Now, to really grasp why we'd ever attempt something so drastic, we need to write out a seriously staggering number in big, bold ink. 3.84 times 10 to the 26th power watts. Think about that for a second. Every single tick of the clock, our sun is converting about 600 million tons of hydrogen into helium through nuclear fusion. It's blasting this unfathomable river of energy out into the freezing vacuum of space. That number right there, that sets the massive stakes for our entire project.
All right, moving right into part one, the astronomical energy waste.
The legendary theoretical physicist Freeman Dyson actually proposed this wild concept way back in 1960. And the core of the problem he saw is so perfectly clear when we draw it out. Imagine a nearly invisible sliver. That represents the 1.74 times 10 to the 17th watts that Earth actually manages to catch. It's literally just a fraction of a billionth of the sun's total power. The rest? A massive, overwhelming amount of energy just lost to the deep cosmos. We are letting an astronomical amount of power slip through our fingers, right when our civilization's energy needs are skyrocketing. Dyson figured out that eventually any growing civilization is going to hit a wall, and to survive, they'll have to capture the entire light output of their star.
Let's turn to part two, shattering the solid shell. If you've ever seen a Dyson Sphere in a sci-fi movie, it's almost always shown as this huge, solid, unbroken metal shell completely trapping a star, which sure, looks absolutely beautiful, but as an actual engineering blueprint, it's completely useless. We literally need to take a massive red marker and draw a giant X through that solid shell idea. Instead, we have to sketch out the only physically viable option, a Dyson Swarm, made up of trillions of independent, ultralight satellites. So, why exactly does the solid shell fail so spectacularly? Well, first off, there's Isaac Newton's Shell Theorem, which proves that a spherical shell actually exerts zero net gravitational force on anything inside it. What does that mean for us? It means the shell wouldn't naturally center itself around the sun. Even a tiny gravitational tug from a passing planet would cause the whole thing to drift, and eventually it would crash straight into the star. Second, to hold a rigid sphere together at 1 astronomical unit away from the sun, you'd need a material with a tensile strength that far exceeds the atomic shear strength of literally any known or even hypothetical material. It would just rip itself to shreds. And third, without massive radiators, that shell would just trap all the sun's heat until the entire structure melted down or straight up vaporized. Bottom line, the solid shell is a total non-starter.
Okay, on to part three, designing the Dyson Swarm.
With that rigid sphere totally erased from our whiteboard, let's figure out what the trillions of satellites in our swarm will actually look like. And spoiler alert, they aren't heavy, clunky space stations. They're mostly heliostats, basically mirrors made from reflective aluminum membranes that are as thin as a soap bubble. What's really fascinating is how they stay in place. A bunch of these mirrors will act as what we call statids. A statit uses a giant solar sail to perfectly balance the outward physical pressure of the sun's light against the inward pull of the sun's gravity. Because they achieve this perfect equilibrium, these statids can just cleverly hover there, completely motionless relative to the sun. That totally bypasses the need for complex, high-speed orbits that could otherwise lead to catastrophic collisions.
Moving to part four, demolishing Mercury for parts.
Now we hit the really crucial question. Where, off Earth, do we find the raw materials to build trillions of giant mirrors? Well, we disassemble a planet. And Mercury is basically the perfect quarry. It has three huge advantages. First, its composition. It has a massive core that is 70% metallic, loaded with iron, nickel, and the silicates we absolutely need to print glass and solar cells. Second, its gravity is only about 38% of Earth's, which means a super low escape velocity, making launching materials incredibly cheap. And finally, its proximity to the sun. Mercury gets 6.7 times more solar energy than Earth does, which gives us an endless, free power supply to run our massive demolition equipment. But hang on, we've got a massive thermodynamic hurdle to sketch out here. Completely dismantling a planet and launching its mass into orbit requires roughly 2 times 10 to the 30th power joules of energy. To put that into perspective, that is roughly 100 billion times the energy that all of modern Earth consumes in an entire year. So how in the world do we get that kind of juice? The secret is exponential bootstrapping.
Picture a brilliant automated loop using von Neumann machines, which are essentially self-replicating robots. Here is how the cycle flows. You have autonomous crawlers strip mining the ore on Mercury. That ore gets fed into massive solar furnaces to be refined. Then, automated 3D printing hubs take that refined material and fabricate ultra-thin mirrors. But crucially, they also print more mining robots. Then, massive electromagnetic railguns called mass drivers fire those newly minted mirrors into space at 4.25 kilometers per second. Once those mirrors hit orbit, they instantly start beaming energy right back down to the factories. More energy means faster mining. Faster mining means more mirrors, which means even more energy. By scaling this loop exponentially, theoretical models actually suggest we could chew up all of Mercury in just a matter of decades, rather than millennia.
Which brings us to part 5, navigating the orbital chaos. With trillions of mirrors now flying into space from our automated factories, it's going to get incredibly crowded up there. And space isn't perfectly still. The gravity from massive planets like Jupiter and Saturn creates this persistent, chaotic tug-of-war. This leads to something called the Kozai-Lidov mechanism, where those distant gravitational tugs can actually warp a satellite's orbit over time. If we aren't careful, that could trigger a cascade of catastrophic collisions or plunge our hard-earned mirrors straight into the sun. To counteract this drift, our ultralight mirrors will just slightly tilt their reflective surfaces. They actually use the physical pressure of solar photons to gently adjust their attitude, meaning they can perfectly correct their orbits without needing a single drop of chemical fuel.
But there's a huge caveat here. We have to make absolutely sure we don't accidentally wipe ourselves out in the process. Imagine drawing the plane of the ecliptic. That's the orbital path where Earth travels. We have to highlight that planetary highway in bright neon green as a strict no-fly zone. We call this the ecliptic gap. Think about it. If we mistakenly blocked even a few percent of Earth's sunlight with our massive swarm, we trigger a sudden artificial ice age and completely collapse our biosphere. So those mirrors absolutely must stay in highly inclined polar orbits to keep Earth safe and bathed in natural sunlight.
And finally, part 6, harnessing the endless fire.
Here is the final glorious piece of our diagram, the payoff. How do we actually convert a trillion points of reflected light floating in deep space into usable electricity back home? We do it through wireless power transmission. Those trillions of mirrors focus raw thermal energy toward heavily shielded orbital hubs. These hubs act like giant converters, taking that intense heat and turning it into focused, coherent beams. We're talking high-frequency lasers or microwave streams, which are absolutely perfect for punching straight through planetary clouds. These beams are then fired across millions of kilometers to massive mesh rectennas down on the surface. These rectennas directly convert the incoming beams into high-voltage DC electricity at an absolutely incredible 80 to 90% efficiency.
Once this staggering power grid comes online, human civilization changes forever. The energy limitations of a single tiny planet completely vanish. We could beam petawatts of energy to warm up the frozen core of Mars and actually terraform it. We could focus our massive laser arrays onto giant interstellar sails, pushing probes to 20% the speed of light so we could finally reach Alpha Centauri. We could even power what are called matryoshka brains, literally sun-sized supercomputers capable of housing quadrillions of digital minds in simulated realities. The possibilities are truly boundless.
Completing this unbelievable multi-generational project fundamentally promotes humanity. We would officially transition from a Kardashev Type 1 civilization to a Type 2 civilization, true masters of our host star. And it's cool because we'd actually leave a universal signature. Since no system is 100% efficient, all those trillions of mirrors and hubs radiating waste heat would cause our sun to glow like a massive beacon in the mid-infrared spectrum, right around 10 microns, for the rest of the entire universe to see.
So as we step back and look at this completed, mind-bending blueprint on our whiteboard, the math actually remains remarkably clear. The required raw materials are sitting right next door on Mercury, waiting to be used, and the physics behind the swarm, it's absolutely sound. Right now, our sun is just radiating its endless energy out into the empty, freezing dark, which leaves us with one final, very provocative question to ponder. Are we, as a species, bold enough to reach out and catch it?
Please like and subscribe.